Another type of reaction, oxidation-reduction reactions. These involve the transfer of electrons. They're called oxidation-reduction reactions, or redox for short. RED from reduction, ox from oxidation. This always reminds me of Redbox, because all it's missing is the B in there. That makes me think about movies, and maybe we could watch a movie, but we need popcorn, and so, yeah, that's how my mind goes. I think they call it redox because ox-red sounds funny. Oxidation or reduction or redox reactions. Redox reactions are very important in everyday life. They go on all over the place. The rusting of iron, the nails in your fence, the metal in your car, those sorts of things. The wrench that the kids left on the fence last summer, that's now just a pile of rust. That's an oxidation-reduction reaction. If you bleach your hair, that's an oxidation-reduction reaction. If you use anything involving batteries, now most of you have something with batteries in your pocket, right, called a cell phone. The battery operates on an oxidation-reduction reaction. And also, many, but not all of them, I'm sorry, that was a bad transition there. Start over. Many redox reactions involve oxygen. Not all of them, but a lot of them. So here's a couple of examples. This is what happens when iron rusts. Iron reacts with oxygen and forms an iron oxide. Combustion is an oxidation-reduction reaction. So here's methane. That's the main component of natural gas. You have to have oxygen for things to burn, right? It burns, it produces carbon dioxide and water. Those are oxidation-reduction reactions. So the way we define oxidation is it's the loss of electrons. So when one compound loses electrons, it is oxidized. Reduction is the gain of electrons. So if one thing loses, the other has to gain. We can't have electrons just appearing and disappearing. So this is helpful to remember which is which. Oil rig. O-I-L-R-I-G. Oxidation is loss. Reduction is gain of electrons. And I still say that in my head every time I look at an oxidation-reduction reaction. Because it's one of those things where you've got two names and two processes, and it's really a toss-up which is which. So you have to have some little mnemonic or trick to remember which is which. You have to have oxidation and reduction occurring together. You can't have one without the other. Because if one loses the electrons, somebody else has to gain the electrons. We're not going to do a lot with redox reactions. All I'm going to expect of you is that you can recognize them. Identify that it is a redox reaction. How do we identify that? Well, if we have a substance reacting with elemental oxygen. So you've got a substance and the other reactant is O2. Remember, oxygen is one of those diatomic elements. So you've got something reacting with O2. That's an oxidation-reduction reaction. If you have a metal reacting with a nonmetal, like you have sodium reacting with chlorine, metal, nonmetal, it's going to be an oxidation-reduction reaction. And then more generally, if one substance transfers electrons to another. So this is the sort of thing we should be able to do. Which of these are redox reactions? Let's look at the first one. 2Li plus Cl2 forming 2LiCl. This is a metal reacting with a nonmetal. This is a redox reaction. So that one is. Let's look at this. What is the charge on lithium here? Does it have a charge? No, it doesn't. This isn't in a compound. This is lithium, the element. These are lithium atoms. Over here, does lithium have a charge? Yeah, it's part of a compound. because lithium chloride is Li plus and Cl minus. How did it come to have a positive charge? It gave an electron to chlorine. It lost an electron. Oil, OIL. Oxidation is loss of electrons. The lithium was oxidized. The chlorine gained an electron. Reduction is gain of electrons. So that's another way to look at this and see, oh yeah, this one didn't have a charge, and now it has a charge. That one didn't have a charge, and now it has a charge. Elements, if you just have one capital letter, it's not a compound. It's just an element, and there's no charge. This is a compound. We have two capital letters. That means there's at least two elements in there. Okay, let's look at this one. Here we have aluminum and tin 2 ion reacting to form aluminum 3 plus and tin metal. How is aluminum going from no charge to a +3 charge? Are electrons being transferred? Yeah, that's what's going on here. This had no charge, and now it has a charge. This has a charge, now it doesn't have a charge. Electrons being transferred, this is an oxidation-reduction reaction. How about C? Didn't fit on one line. Well, first of all, did it fall in one of those two categories I talked about? A metal with a nonmetal? No. Something reacting with O2? No. Doesn't fall into either of those categories. We can also look at this and see, okay, this is an ionic compound. This has a charge. That has a charge. This is an ionic compound. This has a charge. That has a charge. This is one of those precipitation reactions. We just got partners switching. There's no electron movement going on. This is not an oxidation-reduction reaction. How about this bottom one? Yeah. This is something reacting with oxygen. Anytime you have something reacting with oxygen, you're going to have a redox reaction. Okay? Any questions? So that's all you have to do is be able to look at an equation and tell me yes, no, redox or not. Combustion reactions. Combustion reactions are a subcategory of redox. So combustion is characterized by the reaction of a substance with oxygen to form one or more oxygen-containing compounds, often including water. It doesn't have to.
That's where I got.
It is reacting with oxygen, though.
Yes.
So combustion is reacting with oxygen. Often water is formed, but not always. Like in this previous example, this guy down here, that is a combustion reaction, but there is no water formed. But it is combustion because we have carbon reacting with oxygen. And the oxygen thing, I mean, combustion is a word we use, right? Oh, it's combustible. It's flammable, right? What needs to be present for things to burn? Oxygen. That's how you can put out a fire, is by suffocating it, basically. Preventing oxygen from getting in there, the flame goes out. So you got to have oxygen. What happens temperature-wise when something burns? Does it get cold or hot? It gets hot. Okay, we know that from experience, right? Why don't you stick your hand on the stove when it's lit, the gas stove? It's hot, right? You learned that as a kid. So combustion reactions are exothermic. They give off heat. Exo, exiting, thermic has to do with heat. So the heat is exiting, they give off heat. And the combustion reactions we're going to mostly look at are when we have compounds containing carbon and hydrogen, or carbon, hydrogen, and oxygen. These guys are great because they always form the same products: water and CO2. So let's write a balanced equation for the combustion of liquid pentane. And there's no way you would know what the formula for pentane is, so it's given to you there. So here we've got pentane, C5H12. We're just practicing with our state symbols. What's the state of this? It's a liquid. We're told that in the equation. So this is a combustion reaction. What's the other reactant? It's oxygen, O2. What's the state of oxygen? It's a gas. So here we have a compound containing only carbon and hydrogen reacting with oxygen. The products are always going to be the same. Carbon dioxide, what's the state of that? A gas. And water. Now, let's think about this. If you're burning something, like I think you've all at least seen a Bic lighter, right? Do you see drops of water coming out as it burns? No. Is water being formed? Yeah, but it's hot. So the water is in the gas state because it's hot. I will not try to trick you on that, but I just want to explain to you why I'm putting G, because this is an exothermic reaction. When you burn something, it's hot. You can try this at home, like if you have a gas stove or a Bic lighter or a grill or something. Light the flame and then just hold a glass with water in it over the flame. Just, high enough that you're not going to burn yourself or anything, but over it. And what you'll see is condensation appearing on the outside of the glass. That's because as the flame burns, it gives off carbon dioxide and water. And when that water vapor encounters something cool, it condenses. And so that's why a lot of times when you're burning something, you'll see condensation. So these are our products, and we have to balance this. In balancing these combustion reactions, we've got oxygen by itself. Always leave the oxygen for the end, because then you can deal with it by itself. So here we've got 5 carbons and 1 carbon. So I want to put a 5 here. And if you need to write the little tally table underneath, you go right ahead and do that. So 5 carbons and 5 carbons, and then I'm going to deal with the hydrogens. There's 12 of them here. So I need 6 over here. And now I'm going to deal with the oxygens. So I've got 5 times 2, I've got a total of 10 oxygens there, and I've got 6 oxygens there, total of 16. So that means I need 8 pairs, 8 O2s to get the 16 oxygens. Any questions?